Welcome, everyone, to today's Explainer. I am so thrilled to have you here because, honestly, we're looking at one of the most high-stakes, literal, life-saving mechanisms ever engineered. We spend so much time obsessing over horsepower, 0 to 60 times and crazy top speeds, but today, we're focusing on the absolute most important part of any vehicle, the part that actually keeps you alive, the braking system. Okay, let's dive into this. Just picture this totally relatable scenario for a second. You're cruising down the highway going, say, 120 kilometers per hour. Suddenly, a truck pulls out right in front of you. You instinctively slam your foot down on the pedal and your car comes to a screeching, perfectly safe halt. But what literally happens in that one split second between hitting the pedal and the car stopping? How does the 2-ton piece of flying metal just stop on a dime? Well, today, we're breaking the whole shebang down. Here's our roadmap for the explainer. First, the physics of braking. Second, the 4 main braking systems. Third, Pascal's law in action. And finally, some absolutely crucial engineering facts. Starting with part 1, the physics of braking, the journey of energy. Now, what's really interesting about this slide is that at its core, a moving car is essentially just a giant rolling block of kinetic energy. When you want to stop, your braking system has one singular, massive job: tame that energy. But as we know, energy is never destroyed, it has to be converted. So the system takes that kinetic energy of your moving car, uses friction created by the brakes, and converts it entirely into heat. That heat is then dissipated out into the air. That's it. That's the fundamental physics of stopping. Sounds simple, right? But the engineering required to manage all that intense heat safely and efficiently is incredibly deep. Moving right along to part 2, the 4 main braking systems, the hardware of stopping. So how exactly do we make this energy conversion actually happen? Well, there are 4 main categories of braking hardware you'll find out on the road today. We've got traditional disc brakes, older drum brakes, the anti-lock braking system, or ABS, and regenerative braking, which is used in electric vehicles. Let's break these down real quick. First up, disc brakes. This is the most common system in modern cars. Sedans, sports cars, SUVs, you name it. You have a rotating metal disc, called a rotor, that spins right along with the wheel. When you hit the pedal, brake pads clamp down incredibly hard on that spinning disc. The friction slows the disc, which slows the wheel, and bam, the car stops. And this brilliantly illustrates our physics principle from a minute ago. All that friction creates massive heat. Actually, have you ever noticed high-performance sports cars with those drilled holes in their brake rotors? Those aren't just for style. They are specifically engineered to let that extreme heat escape as fast as possible. Now, let's contrast that with drum brakes. This is definitely an older design. Instead of pads clamping down on a disc, you have a drum that rotates with the wheel, and inside that drum, brake shoes push outward to create friction. While disc brakes offer superior high-performance stopping power and way better heat dissipation, drum brakes are far more cost-effective to manufacture. And that simple accounting logic is exactly why you still see drum brakes actively used on the rear wheels of budget-friendly cars today. All right, moving on to our third technology. I want you to just look at the number 15 to 20. Just keep this number in your head, because it represents something absolutely mind-blowing. That number is the secret behind the ABS, or anti-lock braking system. Think about a panic braking situation without ABS. Your wheels can completely lock up. And when your wheels lock, they just slide, and you completely lose the ability to steer the car. It is terrifying. But ABS uses sensors to monitor wheel speed, and the absolute second it detects a lockup, it rapidly releases and applies the brakes. 15 to 20 times per second. Because the wheels keep rotating slightly rather than locking, you maintain steering control. Its true superpower isn't really just stopping, it's letting you steer around that truck while you're standing on the brake pedal. It is a literal lifesaver. And our fourth system is where things get pretty futuristic: regenerative braking. With the massive rise of EVs like Tesla and the Tata Nexon EV, braking has totally changed the game. When you hit the brakes in an EV, the electric motor suddenly acts in reverse as a generator. Instead of wasting that kinetic energy by turning it into heat and just letting it blow away, it converts that kinetic energy into electrical energy and sends it straight back to the battery. You are literally recharging your car just by slowing down. Talk about next-level efficiency. Which brings us to part 3, Pascal's law in action, the fluid mechanics of the pedal. So we know the hardware at the wheels, but what actually connects your foot to those wheels? It isn't just a simple metal cable pulling a lever. It's an invisible, almost magical system of fluid dynamics. So the crucial point is a principle of physics known as Pascal's law. It states that when pressure is applied to a fluid in a closed system, that pressure is transmitted equally in all directions. What does this mean for us? It means the tiny, relatively weak push of your foot on the brake pedal gets transmitted through hydraulic brake fluid and multiplied into a massive, thousands of pounds clamping force at the wheels. It's the reason literally any normal human can easily stop a moving 2-ton machine with just a tap of their foot. And finally, part 4, crucial engineering facts, pro tips for the road. Let's wrap things up with some real-world engineering secrets that actually affect your daily driving. First up is a super dangerous phenomenon known as brake fade. Say you're constantly riding your brakes down a massive, steep mountain. They get incredibly hot. Eventually, the friction coefficient drops significantly because of that intense heat, and your brakes will suddenly feel spongy and terrifyingly weak. This extreme heat is exactly why high-end track and race cars ditch standard steel and use ultra-expensive, highly heat-resistant carbon ceramic brake discs. Now, here is a absolutely vital safety tip regarding that hydraulic fluid we talked about earlier. Brake fluid is hygroscopic. That's a fancy engineering term meaning it naturally absorbs moisture from the air over time. Why is this bad? Because water lowers the boiling point of the fluid. Under heavy braking, the fluid can literally boil, create gas bubbles, and lead to total, catastrophic brake failure. This is exactly why mechanics insist you change your brake fluid every 2 years. It's not some scam to get more money out of you. It is a vital engineering necessity. And finally, have you ever heard that horrible, high-pitched, squealing sound coming from a car's wheels? You know the one. Well, that isn't necessarily a broken part. It is actually a deliberate piece of engineering. Brake pads have small metal indicators built right into them. When the pad wears down to a dangerously low level, that little metal piece starts rubbing against the metal rotor, causing that awful metal-on-metal squeal. It's an engineered warning alarm telling you to replace your brake pads immediately. Seriously, do not ignore it. As we wrap up this explainer, I want you to think about this quote for a second. Power creates motion. Control creates trust. We love big, powerful engines, but brakes are the singular component that makes a powerful machine actually safe to operate. Without that trust, you just couldn't drive. So I'll leave you with this final thought to ponder. Now that you know the deep mechanics of how steering works under panic conditions, do you think ABS is always fundamentally better than normal brakes in every single driving scenario? What's your take on the perfect stop? Think about that the next time you hit the road. Thank you so much for joining me on this deep dive into the engineering of braking systems. Stay curious, keep learning, and I'll catch you in the next explainer.